So in this video, we are going to cover section 3.3, which talks about two different rules that we have for quantifying how much data falls within certain values relative to the mean. We have Chebyshev's rule and the empirical rule. So we're going to start out talking about the empirical rule. So if you remember where we were last time we met, I told you we spent last class defining standard deviation as being this thing that was the standard deviation of the sample was the square root of the sum of the individual measurement minus the average minus the mean, that number squared, divided by the number of samples minus 1. And this was the standard deviation of the data, and it told us something about the spread or the dispersion or the amount of variation in our data. Those were the words that we used to describe that. And I told you that this was a nice number because we could say that most of the data falls within one standard deviation of the mean. And I said that almost all of the data falls within 3 standard deviations of the mean. So now we're getting, and I told you that we would be able to quantify that more in the future. So we're to the future now. We have some now rules that are going to allow us to actually quantify with more than just words like most and almost all. So that's the topic of section 3.3. Okay, so let's start off with the empirical rule. So let's say that I have some data that look like this. No, there we go. And here's a relative frequency distribution of the PCB concentration that I got from sampling 60 different eggs, 60 different pelican eggs. So PCB is this environmental toxin that we actually have a ton of in the Hudson River. And a lot of the cleanup that happens in the Hudson River is kind of dredging the bottom of the river to get out the PCBs. So it's a big problem. One reason that it's a problem is that it makes eggs really thin, and it makes birds unable. Their eggshells are so thin that the birds can't make it all the way through to the hatching stage, and they die before they're born. So here is PCB in some eggs, I think in California, and the mean of this data is that there was 206.45 parts per million in an individual egg, and the standard deviation of that data was 66.42. So I said that last time I said most of the data falls within one standard deviation of the mean. So most of the data is 206 plus 66 down to 206 minus 66. And this is a really nice symmetric unimodal bell-shaped curve. If I were to sort of imagine if I had an infinite number of pelican shells, and I could bend this sort of really, really small and have a really nice distribution. This we could kind of imagine becoming a really smooth distribution. And that's what we do. So what you see a lot of is something that looks like this. So rather than plotting up a frequency distribution that looks like this with the bars and the histograms like what we've been doing, instead of that, we plot this smooth distribution. And the idea with this smooth distribution is that this distribution is sort of this type of a distribution if we had tons and tons of data. So here we sampled only 6 pelican eggs. Say we'd sampled 6 million pelican eggs. Then instead of having to bend between 30 and 70 using this cut point grouping that we're using here, we could have a bin for 30, a bin for 31, a bin for 32, 33, all the way up, and we'd have all of these frequency distribution lines that looked like this, and there would maybe be a little bit of distribution like that. So we could imagine having some sort of frequency distribution, relative frequency distribution, that rather than kind of being jagged like the one that we really have here, is almost smooth. And then we draw a line here to sort of tell us what the smoothness looks like. So I think it's something that's probably overlooked by a lot of books. Like, where does a line that looks like this come from? It comes from having drawn a frequency distribution or a relative frequency distribution and then sort of ignored the bars and drawn a smooth curve around it. Okay, so on this slide, I have the two plots that I've shown you kind of stacked up on top of each other. So we've said here is our data, and here's a sort of smooth bell curve. And these match up pretty well. So this symmetric bell-shaped distribution, frequency distribution, matches up pretty well with this smooth line. In this special situation, the empirical rule applies. So the empirical rule here only use this for unimodal, symmetric, bell-shaped data. Later on in the class, we're going to start calling this something called Gaussian. It's a special shape. So that says, you can't read it because of the glare, that only used for unimodal, symmetric, Gaussian, or bell-shaped distributions. And it says that about 68% of the observations will lie in this range here. And this range is within 1 standard deviation of the mean. So I have about 68% are within 1 standard deviation. About 95% lie within 2 standard deviations. And 99.7% of the observations lie within 3 standard deviations. So if we go back to this review from the very beginning, I said that most of the data falls within 1 standard deviation. For a bell-shaped distribution, when the empirical rule applies, this most is actually 68%. Almost all of the data falls within 3 standard deviations of the mean. Our empirical rule here is telling us that actually 3 standard deviations encompasses 99.7% of the data. Okay, so let's do an example with this. So here's our example that I wanted to look at. So within this data, we found that the mean of the data was 206.45 parts per million. It's somewhere around in here, somewhere between 190 and 230. That's the mean. So I'll label that as X bar. And the standard deviation is 66.42. So 1 standard deviation of the mean away from here is going to go in this direction. And 1 standard deviation below is going to go in this direction, where now what this number is 206 plus 66, which is, carry the 1, about 272. So there is X bar plus 1 standard deviation. And 206 minus 66 is a nice round 140. So here is our 140, and that says that we're going down to X bar minus 1 standard deviation there. So about 68% of our data values fall in this range between here and here. And that looks about right. You know, most of the data, about 2/3 of it, 68% of it, is in those values. Okay, so here is a nice pretty picture of that from your book. So here's the empirical rule for this data, and it says that here's the mean, 206, falls right down here. The mean plus 1 standard deviation is right here. Mean plus 2 standard deviations, that's 206 plus 2 times 66 is up here. And mean plus 3 standard deviations is all the way up here at 405. Mean minus 1, mean minus 2 standard deviations, and mean minus 3 standard deviations. Okay, so we have sort of a number line version of what this is like that says that here's where our values are. So we know that about 68% fall in here, and 95% should fall in here, and 99.7%, also known as virtually all, falls somewhere in here. And actually we see that for this setup, probably all of the data fall within 3 standard deviations. A follow-up question to this is 60 eggs were sampled. How many eggs had PCB concentrations within 1 standard deviation of the mean? So the question is, how many do we expect to find in right here? And so this is an is over of problem. We've done another one of these earlier in the semester. So I like to write this as an is over of problem. So the way that I write this is over of is P over 100. And so I'm going to rewrite this problem. It says, how many eggs had PCB concentrations within 1 standard deviation of the mean? So I'm going to write this to say that within 1 standard deviation, that's 68%. Okay, so 68% is, or 68% of 60 is what? Right. That is sort of how I interpret this question. How many eggs were within 68% of the mean? That's another way of saying that is it's 68% of 60, of our 60 eggs is what number? And now we can kind of read this with our is and our ofs. Here, this 68%, that's the percent that we're looking for. So that goes over here. Of goes with 60, and is what we're looking for. So I can say that x over my of, which is 60, is my percent, 68 over 100. And the easiest way to solve this problem is to cross multiply. So we multiply these two together and these two together. So I can have 100 times x is 68 times 60. And I end up with x equals 40.8. So I expect 40.8 eggs to have PCB concentrations between 140 and 273, because those are the ranges of values that are within 1 standard deviation of the mean. Of course, 40.8 wouldn't be what you would enter online as your answer, because you can't have 40.8 eggs. So we'll round that up to 41. So 41 eggs. And it's approximate. I think the real data for which this came from actually had 43 eggs instead of 41. So all of these estimates are approximate estimates, but it gives you a good ballpark number. About over 40 of our 60 eggs had PCB concentrations between 140 and 273. Okay, so that's the empirical rule, which works very well for nice, beautiful, symmetric distributions that have these nice bell-shaped curves. But what if we have a distribution that looks like this? So the empirical rule is only valid for pretty data. It's not valid for things that aren't nice and neat. So we can't take the mean and the standard deviation of this data and know that 68% of the data should fall within 1 standard deviation. Instead of the empirical rule we're going to use, let's use Chebyshev's rule on some not symmetric data. Here's the written in your book definition of Chebyshev's rule. It says, for any quantitative data set and any real number k greater than or equal to 1, at least 1 minus 1 over k squared of the observations lie within k standard deviations to either side of the mean. That is between x bar minus k times s and x bar plus k times x. I think that's a really overly wordy definition for something that is a lot simpler than that definition makes it sound. So another way of saying that is Chebyshev's rule. So the empirical rule said that 95% of the observations were within 2 standard deviations of the mean. So between x minus 2 standard deviations and x plus 2 standard deviations, 95% of the data fits here for a bell-shaped curve. With Chebyshev's rule, we can actually only say that only 3/4, only 75% of the data is guaranteed for any distribution, no matter how weird it is. 75% of the data is guaranteed to fall within 2 standard deviations of the mean. Within 3 standard deviations of the mean, 89% of the observations are guaranteed for any distribution if it looks like this, or if it looks totally confusing and totally off and totally not symmetric like this. We're guaranteeing that any distribution will fit this rule. So Chebyshev's rule is a more general version of the empirical rule. Chebyshev's rule works on any distribution. The empirical rule only works on our nice symmetric bell curves. Okay, so how did we even get this? So Chebyshev's rule has this 1 minus 1 over k squared fall within k standard deviations to the mean. Okay, so let's just say that k equals 1. Let's put some numbers on here. Okay, so it says that 1 minus 1 over 1, so 1 minus 1 of the observations lie within 1 standard deviation on either side of the mean. So for k equals 1, I have that 1 minus 1 over 1. That equals 1. Minus 1, which equals 0. So what Chebyshev's rule says is that we have no guarantees about within 1 standard deviation of the mean. Okay, so 0% of the data are guaranteed to be within 1 standard deviation of the mean. Okay, so that's what Chebyshev's rule tells us, that we have really no guarantees on that first standard deviation, because we don't know what the data looks like. In the simple case of it looks like a bell curve, we could tell that over 2/3 of the data should be within 1 standard deviation of the mean. But in the general case where we don't know exactly what the distribution should look like, we can't be nearly as rigorous, and we can actually here say that 0 falls in 1 standard deviation of the mean. We keep going with this. Here is k equals 2. So this is what percent of the data falls within 2 standard deviations of the mean. So I do that same calculation, 1 minus 1 over k squared. So that's 1 minus 1 over 4. 1 minus a fourth is 3/4. So that says at least 75% of the data falls within 2 standard deviations of the mean for any data, no matter how ridiculous and not normal it looks. And that's where this number line came from. So it said that 75% of the data for k equals 2, so here's this 2 here is the k. For k equals 2, we do this 1 minus 1 over k squared to find that 0.75, 3/4, 75% of the data falls within 2 standard deviations. Within 1.5 standard deviations, 56% of the data are there. Within 2.5, 84%. Within 3 standard deviations, 89%. And within 4 standard deviations, we're up to 94%. So that's the empirical rule. And So I think on your homework, you have a couple of questions that ask you to determine whether you should use the empirical rule or the Chebyshev rule. So empirical rule, if it's symmetric, bell-shaped, otherwise Chebyshev rule. And you have another couple of questions that are asking you to do some calculations like what we did for the PCB data, where we said, how many eggs fall within one standard deviation. So you're doing this sort of a calculation up here. And that is it for section 3.3.